We're going to start chapter 8 by jumping clear to 8.7, which is about Taylor polynomials, and then we'll come back to chapters 1.6 to 8.1 to 8.6 later. Let's start with this thought. Calculus would be easy if we didn't have to deal with all this sine, log, square root, e to the power stuff, right? If everything was what? Calculus would be easy. I'd say if everything was polynomials. Power rule over and over again, no problem. Would you say calculus would be approximately easy if everything was maybe approximately polynomial? Like if we could just take any old complicated function, treat it as close to enough to a polynomial, and then we could just do power rule stuff on that all the time. So that's a big motivation for talking about Taylor polynomials. So that's one motivation, like I said, take complicated functions, find short, simple function approximations for them. But then also, it's nice to be able to really understand what's going on with functions, and we can see Taylor polynomials and later Taylor series as kind of the DNA of functions. It's like a sequence of things. In DNA, it's a sequence of chemicals, A, C, G, and T. For the stuff we'll be doing, it'll be a sequence of numbers that really describe what's going on with this function and this other function, and we can see how they relate to each other, even kind of how one function might inherit DNA sort of stuff from another function. So that's kind of interesting. Here's some other quick facts about Taylor polynomials. You can see these three things as kind of Taylor polynomials for more complicated things. So the ideal gas law, pressure times volume equals number of moles of gas times universal gas constant times temperature. That's kind of a first order, like a linear approximation, and then we could add quadratic and other polynomial terms to it. Even Hooke's law for spring force, remember I took some data and showed a graph, and it looked like this, where the displacement was here and the force we got was here. And it looked kind of like this. And I said, hey, let's draw a straight line, because that's a straight line through the origin. But we really did see a curve, and maybe a polynomial approximation would have been better, but it wouldn't have been as simple. Let's go and talk about some more about polynomial approximation ideas. Let's say I wanted an approximation for sine of x. I said, hey, Excel can do polynomial trend lines, right? So I can just type in a bunch of data, like use some nicely closely spaced x values from -π/2 up to π/2, and Excel can take sine for each of those, and then I'll just fit a polynomial trend line to it, and we get this. Would you say this is simple? Maybe not really. How would we know, like, what's going on with this 0.9998? Is that really, should that really be 1 or not? Where does 0.1658 come from? These numbers are awfully small. Should I think of them as 0, or should they really not be 0? Is r squared really 1 here? Is that r squared equals 1 would mean that this is an exact prediction of these 300 points, which I don't really think is true. This is about 300 points. What if I did less closely spaced points for the same thing? Notice that the coefficient here, this 0.9997, changes when I change the spacing of the points. Also, I have more precision shown over here. R squared isn't really 1, it's just awfully close to 1. So we've got some problems here, right? That we don't know where these coefficients are coming from. The formulas for doing polynomial trend lines in Excel are really complicated. We don't really understand what's going on. Things depend on the number of points we use. Let's do another approximation. Let's do, again, sine, but now from 0 to pi instead of -π/2 to π/2. This seems like a pretty good approximation, but is there anything we don't like about it? Well, it tends to be a little low here and a little too high compared to the center line here, and a little low there. And also, like here, this black trend line is not curving down as much as the blue is curving down. And then here they're kind of parallel, but the black is a little higher than the midline. And then here the black is actually diving faster than the data is diving, so the derivatives don't even match. And let me just show that the same thing happens when you use more widely spaced data. So let's go write down all those downsides of this idea that we just talked about. So let's see, what were the downsides here? We had no idea where the coefficients came from, so we didn't understand the coefficients. In math, we like to understand things. Maybe that's too much to ask sometimes. So we didn't understand the coefficient values. And the coefficient values changed based on how much data or how closely spaced the data was. That's a decision we'd like to not have to make if we can avoid it. It's actually interesting, the fit didn't actually get any better when we added more data. I didn't talk about that, but it's basically true, which is kind of not what we expect in statistics, right? Usually in statistics, if you add more data, you get better answers, and that didn't happen here in this calculus example. When we went from 0 to pi, we saw the same issues as above. But then we also saw that the slopes didn't even match, and in calculus, slopes are pretty important. So the slope of the trend line didn't always match, and when I say line, I mean polynomial. Didn't always match the slope of the data. That's a pretty big problem. And it was in kind of an unpredictable way. Before we go too much farther in this, I'd like to say, kind of give you the standard warning. Here I was using high order polynomials because I know what I'm doing. I'm a trained professional, right? And we had no experimental error. All this was pure calculation, no randomness at all. If you're doing things where there is randomness in the data, like we do in math modeling and statistics, we really want to avoid higher order polynomials because there's something called overfitting that's a danger. It's trusting your current data so much that you lose the ability to make predictions for any new data that comes in. So we talk about that in Math 319, we talk about that in Stat 360. It's also a big issue in machine learning and data science. They're not with polynomials so much, but other stuff. So even though we're going to be using high order polynomials here in chapter 8, that's because we have no noise in the data at all, and you should really not do that if you have any noise or randomness in the data.